Hi, my name is Ted Pavlik, and I'm a faculty member here in the School of Sustainability and the School of Complex Adaptive Systems, a school where we focus on so-called complex systems, systems where there are many interconnected parts, where we might be able to understand very easily how one part connects to another. But when we look at the spider web of all of those parts together, it doesn't make a lot of immediate sense, at least to our minds. And so we have to make use of computational tools to better understand what's going on when you connect everything up together. And I think a great example of that is epidemics or disease spread, something that I'm sure is on everyone's minds here in 2021, as we're hopefully in the bottom half of thinking about the COVID-19 epidemic. And so you might have heard on the news that people use computer models to make sense of disease spread. And those are the types of things that we teach students how to do in some of our classes here in the School of Complex Adaptive Systems and the School of Sustainability. And so to sort of see how we motivate that, if you look at real data on infection peaks, so the number of people who are infected over time, then you can see for a disease like Ebola across different locations where Ebola breaks out, then you end up getting a similar pattern where you get a sharp peak in the number of people who get a disease, followed by usually a sharp decline. And if you look at COVID-19, you can also see some of these peaks, and sometimes you might get secondary peaks and so on and so forth. So really what we want to do is to be able to understand where these peaks come from. And if we have a computer model that can produce similar peaks, then that allows us to sort of be a playground on which we can investigate how to make changes that, if they work in the computer model, might then work out in the real world. So that's what we want to try to get to here. And one of the simplest models is the so-called SIR model that you might have heard about in previous classes, or maybe in the movies, or maybe in the news. And so this is a simplistic model of disease spread, but there is some aspect of this model in pretty much every real world disease we see. You can embellish this model, make it more complicated, and so on and so forth, but at least some aspects of the dynamics of this model are present in disease spread in general. And so the basic idea is, when you think about disease, you have to start out with three populations. And those three populations are the population of so-called susceptibles, the population of those who currently have the disease and are spreading it, the infectious population, and a population of those who have had the disease and carry some immunity. And so this is where we get the SIR of this so-called SIR model. Now, don't want to go into a lot of details here, but the basic idea is, once we have on our kind of bookkeeping that these three populations, we can write some simple mathematical expressions that help us understand how people in one population move into one of the other subpopulations over time, based on the probability that they will encounter someone in one of the other subpopulations. So as an example, this diagram here is a graphical depiction of some mathematics behind the scenes that represents a so-called contagion positive feedback loop. The idea here that if you have one infectious person, then it's unlikely they're going to meet many other people and infect them. But if you have a lot of infectious people, then there is a high likelihood that they will infect people at a high rate. And so there is a positive feedback here, where once people start to get infected, then over time, even more and more and more people start to get infected. So we refer to that as a positive feedback loop. Now, if we look at these infected population, eventually they're going to recover. And so after some delay while they're sick, then they eventually become part of the recovered population. And so we have mathematics behind the scenes that represents how long that happens, and that keeps track of how many people are in these two boxes. And then finally, just like the number of infected is going to be depleted as they move into recovered, the number of susceptibles are going to be depleted as they move into infected. And so as more and more people get infected, there will be eventually less and less people to infect. And so we have to model this negative feedback loop of the susceptible population declining over time. So as systems theorists, when we draw all this out, then suddenly we look for these patterns of loops. We see that there is a negative feedback loop right next to a positive feedback loop. Well, we know as systems theorists that generally means that the decline that we see in the susceptible population isn't going to happen forever. It's going to eventually round off, and it's going to look like what we refer to as S-shaped growth. It'll look kind of like an S. And then likewise, when we look at this contagion loop next to the recovery loop, that's another one of these things where we have a positive feedback loop right next to a negative feedback loop. And that tells us that the growth in the the growth in the recovered population will actually initially be very rapid, but eventually will round off as we deplete the infected population. Now, those seem like very simple patterns, but putting them together ends up being something that sometimes it's hard to think through. So when we put those two S-shaped growth patterns together, which is what you can kind of see plotted back here, you see the S-shaped susceptible population declining over time. You see the S-shaped recovered population growing over time. And when we keep track in the computer model of what the infected and the number of people infected does over time, we see that it grows, it reaches a peak, and then it falls off. In other words, it does produce the infection peak that we were looking for, that we're so used to seeing in real world data about real epidemics that spread. So this gives us confidence that maybe we have a toy model that actually is a stand-in for the real world, so that we can start investigating that toy model, breaking it, changing it, in order to sort of do scenario planning for how to deal with what's going on in the real world, in this epidemic and in the next one. And so when we look at these models, we start making observations. Like, for one, in the toy model, we notice that the infection is going to die out before everyone is infected. So we initially had so many susceptibles, but if we look at the kind of final number of recovereds, the final number of recovereds is less than the initial number of susceptibles, which means there's going to be a small population of susceptibles that never actually experiences the disease before the disease dies out. This is the so-called herd immunity that you've heard about, that a lot of people are counting. Now, when we talk about herd immunity, then we want to quantify how likely it is that herd immunity happens in a short amount of time, and how big this protected population is going to be. So the question is, how do we wrap our minds around predicting how big this population is going to be? So what conditions determine how big this population is going to be? And when we look back and think at our model, we think about, in terms of our model, what we're really asking is, how does the infection rate compared to the recovery rate? Because we have these two processes: the susceptibles becoming infected, that's the infection rate, and the infected becoming recovered, that's the recovery rate. And so we kind of get the impression that we need to sort of pit these two things against each other and see if we can take these two rates, and if we can somehow compare them, maybe we can predict how big this herd immunity population is going to be. So when we do that, we sort of say, well, we've got these parameters in our model that we can measure from data out in the real world. We've got infectivity. How likely is it that a sick person's going to get a susceptible person they meet? How likely will that cause disease to spread? We've got contacts per day. How much is the population churning around, causing infected people to bump into susceptible people? And then we've got our duration of infection. When you're sick, how long are you sick, and how long are you spreading the disease? When we put all of those things together, we can then start creating little measures that help us better understand how this model is working. So we can multiply the infectivity, how likely it is and disease will spread on and contact, with contact rate. And that kind of tells us how rapidly at any instant of time the infection will be growing. But then likewise, if we want to figure out, well, how rapidly is the infection decaying, then in that case, we can just do 1 divided by the duration of infection. That kind of tells us, for every person who's infected, then how long do they stay infected? And so these are kind of like per person. So every individual who's infected, how quickly are they infecting others, and how quickly are they recovering themselves? And when we put those together, now we can ask, which one of these rates is bigger? So when you put that together, you get, this is something you'd see in an algebra class or something like that. You've got one rate on the left-hand side, one rate on the right-hand side, and you just ask which one's bigger, the infection rate or the recovery rate. And with a little bit of manipulation, then you get this funny little term over here, infectivity times contacts per day times duration of infection. And that is something that you probably have heard about in the movies, the so-called basic reproduction number, or R naught. And that R naught is something that usually you hear people comparing to 1. And you can interpret this R naught as to basically be, on the rate side, it is the relative, it's sort of how frequently an individual infects others divided by how frequently they clear their infection. So it's sort of a proportion of clearance rate that the infection rate is. Another way to view it is how long one person is infected divided by how long until an infected individual can infect another. So in both of these sort of interpretations, you kind of want this number to be less than 1. And that kind of tells you that the clearance process is going to be dominating versus the infected process. Now, those things are kind of a mouthful. And so a lot of people, when they talk about R naught, they say, at the beginning of a disease, before anyone is really infected, then R naught represents the average number of new infections caused by each individual during her infectious period. So when we think about 1, that means that while someone's infected, they infect one other person. And so if that continues on forever, then the disease would never go away. If it's greater than 1, then while someone's infected, they get more than themselves infected. They get 2 other people infected. So even though they get better, they've left 2 people who are now worse. If it's less than 1, then that means on average that while they're infected, then they might not actually infect anyone. Some of them might infect 1 person, and on average, the average infected person infects less than 1 person, and that causes an eventual decay. So that's where people get this so-called R naught rate that you might have heard about, or basic reproduction number. It is the product of these 3 factors: infectivity, contacts per day per infection person, and duration of infection. And if it's less than 1, then an infection is going to die out naturally. If it's greater than 1, then it's going to spread through a population. And that little herd immunity population, that, crazily enough, is just 1 divided by R naught. That fraction of the population is how many people at the end of the epidemic are going to get away without actually getting sick. So policymakers, when they think about long-term disease planning, they focus on these 3 factors: infectivity, contacts per day, duration of infection. How can we come up with therapeutics that reduce the duration of infection? How do we come up with quarantine policies that reduce the contacts per day? How do we best understand the infectivity of diseases as they come by? And based on what we know about all of those things, we can come up with tables of these R naught values. And these tables tell us that if a particular disease were to break out, how many people do we need to get vaccinated to feel like we're safe from the disease continuing to spread, for example? Or if we don't vaccinate anyone, then how long is it going to be until we reach a natural die out of the disease? And so this all comes from looking at diseases through the lens of systems theory. So when we talk about how computer modeling helps us fight, say, COVID-19, then what we're doing, and this is taking the words from a reporter who's quoting from researchers, is that we are using modeling to be directing the way in which we are trying to think about diseases. And it helps us identify directions that may not have been clear before we formalize these simple models. These are relatively simple models, certainly in real life. Other processes are going on, and we can add those complexities, we can trickle them in over time. But if we start with the basics, it really makes sure we've got our fundamentals right up here. And that ends up making us make much more better informed decisions when we actually go and intervene into the real world. And those are the types of things that we like to teach our students here in the School of Sustainability and the School of Complex Adaptive Systems. And if you're interested in learning more about this, a lot of my classes I put online, you can go and Google for them. Otherwise, take a look at our course offerings here at ASU, and have a good day and stay safe.